grad students here, I shelf, and it's been there for a long time, and he promised the students that if they ever got some efficiency, I've forgotten the number, call it 20%, he would eat the apple. And I was there for 5 years, and he never ate the apple. It was really looking bad at the end of the so I don't know if he ever had to eat the apple or just left to start some power.
Disappeared.
But we're all waiting to see that happen anyway. But Richard obviously is a world expert. He's at Spectrum Laboratories. He's co-founder and editor of the Journal of Photovoltaics, and he's general chair of the next Photovoltaic Specialist Conference, the big conference in this field. So I'm very delighted to have you, and so without further ado, Richard.
Well, thanks very much for that introduction, John. And thank you all for coming this afternoon. My talk today, I'd like to talk about novel semiconductor materials for high efficiency multi-junction photovoltaics. And I'd like to first of all thank my collaborators at the National Renewable Energy Laboratory, University of Illinois, Fraunhofer Institute, University of Michigan, and the whole multi-junction solar cell team at Spectralab. And the outline of my talk today is, first I'd like to talk about the big picture, what motivates a lot of this work, theoretical solar cell efficiency limits, and look at some unifying behavior in semiconductor energy levels, and look at the electronic activity of defects in semiconductor families. And finally talk about multi-junction solar cells and some applications in concentrator photovoltaics. So this is a chart. Thank you, Tamara. So this is a chart on, let's see, put together by the Intergovernmental Panel on climate change, showing the
It's only for the taping, it's not for the...
Oh, okay, so I should speak louder, it sounds like. Okay. So this is the deviation from the average temperature. Oh, excellent. Thank you. Thank you, John. So we've had fairly constant temperatures over the last 1,000 years. You can see we're entering this hockey stick regime where fossil fuels are contributing dramatically to global climate change. So this is our challenge. In addition, imported fuels have a big cost in terms of political stability and national security. So photovoltaics offers a potential way to get around those problems since it doesn't emit greenhouse gases. Photovoltaic solar electricity combined with power storage in plug-in hybrid vehicles and long-distance power transmission from sunny parts of the country to places where demand is highest can all be part of a solution to the problems that we're encountering with climate change. So that's one of the biggest motivations personally for me in looking at all of this. So theoretical solar cell efficiency limits. Shockley-Queisser wrote a very famous paper that you're probably familiar with on the detailed balance limit of solar cell efficiency. And one of their assumptions was using single junction solar cells. For a single junction solar cell, the maximum efficiency one can achieve with the assumption of one electron hole pair generated per photon is 30%. And for a device with a single cutoff energy, it's 44%. And that's due to the phenomena that I'm sure you're familiar with. Photons with energy below the band gap can't contribute to photogeneration. They can't contribute to the current of the solar cell. And for photon energies above the band gap, you have a photon utilization efficiency that drops off because these higher energies are not able to be fully utilized by a material with a single band gap. So the paper by Shockley and Queisser, which continues to be relevant today, made several important assumptions, and they were quite explicit about which assumptions they were making. One interesting way of viewing this is that these assumptions also represent opportunities for making higher efficiency solar cells. And many of the high efficiency solar cell architectures that we're entertaining today are based on overcoming one or more of these assumptions that Shockley and Queisser made. So for instance, for the assumption of a single bandgap energy, we're of course addressing that with multijunction cells. The assumption of one electron hole pair per photon, that can be addressed through avalanche multiplication or multiple exciton generation. The non-use of subbandgap photons can be addressed by the use of upconversion. Having a single population of each charge carrier type, holes and electrons in their respective bands, is addressed by hot carrier solar cells, and so on. But in this talk, we'll talk mainly about the multijunction solar cell approach. So Henry also talked about the detailed balance limit, but applied it to multijunction cells and also applied it to concentrator solar cells. So for example, a standard type of solar cell made today is a 3-junction solar cell with gallium indium phosphide, gallium indium arsenide, and a germanium bottom cell, which also serves as the growth substrate. So the theoretical efficiency of a 3-junction cell, for instance, is now up to 56%. And you can see the advantages of going from a 1-sun concentrator cell. The concentration brings that one single junction efficiency up to 37% instead of 30% at 1-sun. Adding another junction brings us up to 50%. 3 junctions brings the theoretical efficiency up to 56%. And having an arbitrarily large number of junctions, Henry modeled the case with 36 junctions, so which is getting close to infinity in this case, of 72% efficiency modeled. And the reason for that, of course, is because we're now using the broad wavelength range of the solar spectrum more efficiently. So we now can use the photons in each of the wavelength ranges of the respective subcells and use much more of the spectrum. So in order to do that, we need to identify subcell materials that have a number of different band gaps. And we need to do those at the same lattice constant, ideally, if we're going to grow a lattice-matched structure. The search for materials of the appropriate band gap at the appropriate lattice constant often leads to a case where we have unwanted defects in the semiconductor materials. So one very interesting aspect of research in semiconductor materials for solar cells is the defect energy levels and their recombination activity. And a lot of the slides coming up next will deal with that. So quite a bit of earlier work has observed the tendency for some of these defect levels to form at a nearly constant energy in different semiconductors, in different semiconductor families. So I'm sure you're quite familiar with the work by Chris van der Waal. Sorry about that. Where a theoretical study done by Chris van der Waal showed that there was universal alignment of the energy levels of hydrogen atoms in semiconductors. They found that for 3,5 materials, 2,6 materials, even for electrolytes. There's also some interesting work in these chalcopyrite materials, copper indium diselenide and related materials, finding evidence for a bulk reference level that stays at a constant distance from the vacuum energy level, even as the group 6 composition is varied. And Volukovits has done some interesting observations of the Fermi level stabilization energy, in which we'll talk about a little bit more, in which defects formed by damage to the lattice also tend to appear at the same distance from the vacuum energy level. So these observations indicate that there are some common defect configurations that result in a near constancy of energy level. And these trends, which are universal among semiconductor families, have some power to explain and predict the doping properties of defects in the same semiconductor family. For instance, considering wider bandgap chalcopyrite materials compared to the parent material of copper indium diselenide, and even looking at different families. So some aspects of copper indium diselenide may even apply to gallium indium nitride, both being polar covalent, covalently bonded semiconductors. So the theoretical work done by van der Waal shows these constant hydrogen energy levels for a whole host of these semiconductor materials. So you can see that all of these are lining up very convincingly and somewhat surprisingly a constant difference in energy from the vacuum energy. So this brings up a number of questions. To what extent and in what circumstances do the energy levels of certain defects mirror that constancy of hydrogen atom states in different semiconductors? And does this behavior establish the tendency for some types of defects to form near a specified energy from the vacuum level? If so, that would be very powerful in understanding these defects better. So in another paper that sheds some light on this, changes in capacitance and frequency and temperature allow the extraction of defect energies and densities using admittance spectroscopy. And this leads to a clear picture of the evolution of the defect energies in copper indium diselenide materials as one varies the sulfur and selenium composition. So those results are shown here as a function of sulfur composition. The trap energies due to native defects are approximately constant with respect to the vacuum level, and they, as one changes this sulfur composition, increasing the sulfur composition increases the band gap. So now these trap energies, instead of being very near the band edge, are now closer to the mid gap, and therefore have higher recombination than they did in the gallium and the copper indium diselenide. This is one of the challenges, but not the only challenge associated with finding a high band gap chalcopyrite material that could be used potentially in tandem to make a multijunction cell in combination with the 1 EV copper indium diselenide. So to add to our list of questions, to what degree does the reference bulk defect energy level observed in 136 chalcopyrites extend to other semiconductor families? And what does this behavior say about the recombination at defects in different host semiconductors? And of particular interest are the very low recombination activity that's observed in materials such as copper indium diselenide and gallium indium nitride. Copper indium diselenide has extended defects that are nearly benign in terms of their recombination activity, which is very intriguing and of course would be very desirable to replicate in other new semiconductors. So there's also this concept of the Fermi level stabilization energy, where damage to the lattice forms defects at about the same energy with respect to the vacuum level. For instance, in this case, as one changes composition from gallium nitride to indium nitride in the gallium nitride system, which many of you are extremely familiar with, that Fermi level stabilization energy goes from being a state near, well, that's in the gap, to a state that's in the conduction band, and as a result becomes far less active in terms of its recombination activity as one increases indium composition. So a little bit different flavor of common themes among different semiconductors, but one that still shows the tendency for materials to have a constant behavior even among different semiconductor compositions and families, is this concept of a bandgap voltage offset, or WOC. So an observation that many of us have made is that if one plots the open circuit voltage for semiconductors for a wide range of compositions and a wide range of band gaps, the difference between those two, the band gap voltage minus the open circuit voltage, turns out to be very constant among lots of different types of semiconductors, and spanning this whole range of useful band gaps for making multi-junction cells. So the open circuit voltage is shown in green, the band gap is in blue, and as a function of band gap, this band gap voltage offset is very near 0.4 to the 0.5 range for a wide range of semiconductors. And that has to do with the similarity of density of states in the conduction and the valence band. So when you're working with multi-junction cells and you have a large number of band gaps that you're dealing with, the diode saturation current density, J0, can vary widely depending on that band gap. So it becomes harder to gauge whether you have a good J0 or not so good J0, because that changes so much with band gap. If you put some of these classic semiconductor equations into a formulation that uses W, the band gap voltage minus the cell voltage, one can, for instance, transform this familiar expression for the PN product into a form which no longer involves this somewhat artificial parameter of intrinsic carrier concentration, to much more physical parameters, the density of states in the conduction band and the density of states in the valence band. So the PN product then has this form when you put it in terms of W, the band gap voltage offset. Similarly, you can, instead of the emitter saturation current density, which is related to open circuit voltage in this way, one can define a different parameter, K0, which is just the emitter saturation, or the diode saturation current density divided by n sub I squared, which again involves the more physical densities of states in the bands and the band gap voltage offset. So this can be quite useful when dealing with cells of multiple band gaps. So each of these observations of some form of constant that applies across semiconductor families can reveal a fairly profound unifying aspect of the fundamental nature of these materials. And connections between these defect energies may help us to understand fundamental principles that lie behind the remarkably low defect recombination activity in some types of semiconductors which we mentioned before, such as copper indium diselenide and gallium nitride. So finding answers to these questions will help us understand at a deeper level what makes these semiconductors tick. So I'd like to talk about a few of these different semiconductor material systems. Very important is how you grow these materials, of course, and the defects that are introduced by the growth process. Some of the more interesting material systems that we've worked on at Spectralab for their ability to tune the band gap of subcells to form a better match to the solar spectrum in multijunction cells are these metamorphic 3,5 materials, or lattice mismatch 3,5 materials, dilute nitride gallium indium nitride arsenide, which can include antimony in the composition, and polycrystalline 136 and related materials. So there's this Chalcopyrite family, which can include a wide range of alloy compositions, including silver and aluminum, sulfur and selenium. We often just refer to that as SIGs, that whole family. And Keisterites, which replace the group 3 by a combination of this group 2 and group 4. And a new class of solar cell materials, which has been very exciting lately, Perovskites, which have had a remarkable rate of progress in the short time that they've been being researched. They're now up to 12% efficiency with a relatively short period of time in their development. But they are organic semiconductors involving a methyl and amine and a lead halogen composition. So one of the main ways that we've used at Spectrolab to grow our materials is organometallic vapor phase epitaxy, or as many people like to call it, metal organic chemical vapor deposition, or MOCVD. I think many people are very familiar with this process. We introduce our metals in the form of organometallics. Molecular beam epitaxy, of course, is very useful for very controlled samples, and we can monitor the layers growing one atomic layer at a time through read patterns such as this. For growing some of the more experimental and more highly defective polycrystalline compound semiconductors, like copper indium diselenide, we often use selenization and sulfidation reactions to form SIGs and the Keisterites. So they're a relatively simple setup in which metals are deposited onto molybdenum film on glass typically, and then the copper, gallium, indium, and other precursor metals associated with the SIGs solar cell material are deposited, and then those are reacted in a hydrogen selenide or hydrogen sulfide ambient at elevated temperatures. So it's a relatively simple reactive furnace setup that can result in some remarkably high efficiency solar cells. So being polycrystalline materials and being materials that are formed in a somewhat non-ideal but also intriguingly a low-cost method, these materials can have a high density of dislocations, both extended defects, grain boundaries, and point defects within the grains. So we use a variety of techniques: deep level transient spectroscopy, admittance spectroscopy, both in the light and the dark, time resolved photoluminescence to measure the lifetime of carriers directly. And also we can get a better idea of the atomic configuration of these defects with techniques such as transmission electron microscopy, atom probe tomography, AFM, and FTIR is quite useful as well for getting to the bottom of what is the actual structure of these defects. So talking about metamorphic 3,5s, first of all, this is a plot of multi-junction cell architectures going from about 40% efficiency up to 50% efficiency. And so first off, a fairly standard 3-junction solar cell, which is now a production terrestrial concentrator solar cell, is shown in schematic here. It has a transparent metamorphic buffer, that transitions from the larger lattice constant of the germanium substrate to the lower lattice constant of the upper cells. And in this way we can achieve a lower band gap in the upper cells, which is advantageous for this specific spectrum that we have coming from sunlight. Those type of cells have, in practice and in this model, a production average efficiency of about 40% these days. So an example of some of those cells are, we have cross-sectional TEM of some of those cells here. The germanium substrate is here. We grow a step-braided buffer, and because of the lattice mismatch, there are unavoidable misfit dislocations. But the metamorphic buffer is designed to minimize the threading segments of those dislocations. So we can actually manage to achieve active solar cell layers up here in the active gallium phosphide and gallium arsenide solar cells that have remarkably low 2 times 10 to the 5 per square centimeter dislocation densities. Another way we can visualize the metamorphic structure is through reciprocal space mapping, X-ray diffraction reciprocal space mapping. There's the substrate, the germanium substrate is shown here. Here's our metamorphic buffer extending out to this new lattice constant of the gallium arsenide middle cell. And this buffer is designed to lie almost completely on the line of 100% relaxation. That 100% relaxed step-graded buffer removes the driving force for dislocations to propagate into the upper cell layers. And the result of that is we can grow metamorphic solar cells with a wide range of band gaps that retain a fairly high minority carrier collection efficiency out at these longer wavelengths that we need to convert the solar spectrum. So starting with gallium arsenide here at about 1.4 eV, you can see that even when we get out to 1.6% lattice match or over 2% lattice match, which is quite a large amount of lattice mismatch, we're able to get out to 1.1 eV or even below 1 eV and still have quite good minority carrier collection, indicating long diffusion lengths in these metamorphic materials. So it almost gives us the ability to change this band gap at will. Some more examples of characterization in this 23% or about 1.1 eV gallium arsenide. We image defects with photoluminescence and also with plan view transmission electron microscopy. Both are giving pretty good agreement of dislocation densities in the 3 to 4 times 10 to the 6 range for this composition. So it's encouraging that these are agreeing with each other. We've also done studies where we vary the composition, vary the amount of lattice mismatch. As you can see, with more lattice mismatch, we are encountering more defects. But very significantly, not only does the dislocation density go up, which is shown in blue as we increase the indium composition, but the effectiveness at each dislocation at mediating recombination also increases. So this is the percent carrier loss at each dislocation. So you can see that each dislocation is, in addition to being more abundant, they're also more effective at causing recombination, unfortunately for us. These are some time-resolved photoluminescence curves in gallium phosphide and in gallium arsenide. So these were time-resolved photoluminescence measurements done on double heterostructures grown at Spectrolab, and the TRPL measurements were done at the National Renewable Energy Laboratory. So we can see minority carrier lifetimes up to over 2 microseconds in these materials, which is quite long for a direct bandgap semiconductor. this just shows the way that the minority carrier concentration drops off with increasing lattice mismatch. Also shown here is the difference in minority carrier lifetime for both ordered gallium indium phosphide and disordered gallium indium phosphide. There seems to be some difference, though not a large difference, in the lifetimes in those ordered and disordered materials. But I'd like to just talk for a moment about sublattice ordering also, because that's another important way to control the band gap of the wider band gap gallium indium phosphide materials that are used in multijunction cells. So in fully ordered gallium indium phosphide, we have 111 planes that either have all indium or all gallium, as you see in this crystal structure. If you look at these atomic components of the 111 planes for a moment, in fully disordered gallium indium phosphide, you can see now that those 111 planes have a random combination of gallium and indium on each of the 111 planes. So the composition of the gallium indium phosphide is the same, but the band gap can shift as a result of this disordering on the group 3 sublattice on these 111 planes. So the band gap can go up by 100 millielectron volts as a result of disordering these gallium and indium atoms. That turns out to be very important to achieve a higher band gap top cell in multijunction cells. It's very advantageous to be able to achieve that higher band gap. And the way that arises is stresses in the growing crystal caused by phosphorus dimers that form on the surface provide the thermodynamic driving force for ordering. So mechanisms that disrupt that can result in disordered material and result in a higher band gap, more desirable top cell. We can measure this gallium indium phosphide ordering directly using the 1/2 115 X-ray diffraction peak. So for instance, this layer is largely ordered. We're able to see that peak coming from the 1/2 115 reflection, and this we see very little ordering. So this film is mostly disordered, and as a result, the band gap in this case goes from 1.81 to 1.89 eV. So gallium indium nitride arsenide is a very interesting material, as I mentioned briefly earlier. One of the main advantages of that is that gallium indium nitride arsenide has an unusual and also very useful property that when you add this smaller atom of nitrogen, instead of making the band gap go up as it does with a small atom like phosphorus, the addition of nitrogen makes the band gap go down. So adding nitrogen to a gallium arsenide base composition can allow us to achieve band gaps in the 1 eV range, even at the gallium arsenide lattice constant. So we compensate the smaller atom of indium with the larger atom, the smaller atom of nitrogen with the larger atom of indium. We can keep the lattice constant the same, and yet both of those drive the band gap down. So we can use the gallium indium nitride arsenide in a multijunction cell in this way. There's a real scarcity of appropriate semiconductor materials with this 1 eV band gap at the gallium arsenide lattice constant, which this gallium indium nitride arsenide fills. Unfortunately, and I'll just point out that with a 5-junction cell of this type, we can reach a 47% efficiency, at least with realistic modeling. That's far from a theoretical efficiency. The problem is that this dilute nitride material has a number of defect levels which form in it. There's 2 defect levels that are seen consistently by DLTS. One important one is this electron trap, which stays at about 0.9 to 1 eV above the valence band as nitrogen is added and the band gap decreases. So that, unfortunately, becomes more benign. It becomes more shallow near 1 eV. There's a second defect level follows the lowering of the conduction band and stays near the mid gap, and that's more problematic. In terms of the identity of the defect that's formed in gallium nitride arsenide, one very interesting result from modeling is that the presence of hydrogen greatly decreases the formation energy of this defect complex, this nitrogen-hydrogen gallium vacancy defect complex. So you can see the formation energy is way down here. So when you have hydrogen around, this defect is fairly easy to form. It acts as an acceptor, and it's thought that this may be one of the main fundamental defects in gallium nitride arsenide. Positron annihilation spectroscopy also shows that when you have hydrogen present during MBE growth of this material, you also have a increased concentration of gallium vacancies. So the positron annihilation allows us to measure those gallium vacancies directly. So in these gallium nitride arsenide films, we can achieve really quite good internal quantum efficiencies. So internal quantum efficiencies well above 90%, making this definitely a very viable solar cell subcell material to use in a multi-junction cell. Those were dilute nitride cells grown by MBE, but the dilute nitride materials can also exhibit good internal quantum efficiencies when grown by metal organic vapor phase epitaxy as well, or MOCVD. But the annealing and the thermal history have a strong influence on the quality of the gallium nitride arsenide. One study that we did was on Fourier transfer infrared spectroscopy of these defects in dilute nitride. And in this paper by Sarah Kurtz, we looked at these FTIR spectra. We could, as grown, we see that this peak at 467 inverse centimeters corresponds to nitrogen bound to gallium primarily in a gallium-4 nitrogen configuration. However, after annealing, we see a higher fraction of that nitrogen being bound to indium in a gallium-3 indium nitrogen configuration. So that's very significant for the recombination in the material. The shift of this peak also seems to be correlated to hydrogen forming bonds with nitrogen as we anneal, and that's also thought to be one of the more important defects controlling recombination in the dilute nitrides. So this is just schematically the nitrogen is shifting over its position in the lattice to be closer to indium as a nearest neighbor upon annealing. So another important change with annealing in gallium nitride arsenide is that as grown, chain-like columnar nitrogen ordering occurs, and you can see the strain fluctuations caused by this ordering in these TEM images. After annealing, so these are sequentially increasing annealing schedules going from as grown to annealed and more annealed. You can see that the gallium nitride arsenide is becoming much more homogeneous, and so it's breaking up these nitrogen chains, which is also very beneficial. So shifting gears to chalcopyrites, a very interesting semiconductor material. We can form these chalcopyrites from all of the elements shown here. Copper, indium, diselenide is the most common example, but we're also very interested in some of these elements that involve smaller atoms because they result in higher band gaps for the multi-junction cells that I was talking about earlier. So in the SIGS device, the absorbing layer is typically a copper, indium, gallium, selenide alloy. It has remarkably low recombination at extended defects. There's good window layers available. We typically use molybdenum for stability. And here's the way the band diagram looks as you go through the device, as well as the actual device itself. So the window, the copper indium diselenide absorber, as you can see, full of grain boundaries which don't really seem to impact device performance that much, and the molybdenum contact. So some questions here are what is the major recombination center? I think maybe I'll skip over some of this work in the interest of time, except to say that a very interesting observation by Angus Rocket at University of Illinois is that these layers facet spontaneously into polar 112 type planes, which is very interesting that the polar planes are stabilized and preferred. So these preferred planes seem to be relatively inactive. They're extremely passive 112 surfaces, and this is related to the recombination inactivity of the extended defects, but needs to be understood more fully. Perovskites is another very interesting semiconductor material, very defective, but yielding very high efficiencies somehow. Present perovskite-based solar cells evolved from the dye-sensitized solar cell architecture, which some of you might be familiar with. That architecture involves a porous titanium dioxide lattice on which the absorber materials, which is dye in the case of dye-sensitized materials, and perovskite in the case of the perovskite cells. These cells can have a very simple types of processing. So again, I think I'll skip through some of this work, but the perovskite, in the perovskite materials, a large amount of the electron transport has been seen to go through the perovskite itself rather than into the titanium dioxide. And that's related to some of the very high efficiencies of 12% or so that have been seen.
How's the reliability of these cells?
Oh, I think that's still an issue. That it's still very early on, but they will degrade with moisture. So.
But they don't show the UV degradation of the dye-sensitized?
I'm not sure about that. It's a relatively new material system. So, but one very appealing thing about them is that the perovskite absorber can be placed on top of, has a fairly high band gap, so it can be placed on top of, for instance, a copper indium diselenide low band gap material to form multi-junction one-sun cells, which would have much higher efficiency than today's single-junction silicon cells potentially. So I wanted to get to the point where we can talk a little bit about multi-junction cells. This is a structure of 3-junction lattice-matched cells and 3-junction metamorphic cells, which we've already looked at a little bit. And this is the plot which you've probably seen quite a bit of, where the National Renewable Energy Laboratory has kept track of best research cell efficiencies. So the early 3.5 multi-junction cell development at Spectralab took us from 32% to 41.6% efficiency along this part of the multi-junction cell efficiency plot. That metamorphic cell design resulted in the first solar cell of any type to reach above 40% efficiency, and efficiencies have now reached 41.6% for both metamorphic and lattice-matched 3-junction cells. So the quantum efficiencies of the constituent subcells of that 3-junction cell are shown here. This is the lattice matched case. And then for metamorphic cells, you can see the lower band gaps have shifted us down in wavelength, allowing us to use the solar spectrum more efficiently. So another very interesting recent development has been solar junctions, 3-junction cell with a dilute nitride bottom cell at 44% efficiency. It has a cell structure like this with gallium indium phosphide, gallium arsenide, and 1 eV dilute nitride on the bottom. And yet another very interesting recent development is the use of wafer bonding that Soitec and Fraunhofer have used to form a 4-junction semiconductor bonded cell. That has reached 44.7% efficiency. And another recent result that Spectralab has achieved recently is a 1-sun cell result, also using wafer bonding. But this is a 5-junction cell, and it's at 1 sun, so the efficiency is lower, but it's a record efficiency at 38.8% efficiency. And the structure of that cell is shown here, 5-junction cell. And you can see the cell construction a little bit more clearly on this plot. We start out with 2 different substrates, with a gallium arsenide substrate and an indium phosphide growth substrate. We grow the upper 3 cells inverted, and we grow the bottom 2 cells upright on the indium phosphide substrate. That cell is then flipped and bonded to the lower combination of subcells. We then remove the growth substrate, the gallium arsenide growth substrate, put on the metal grid, and then we have a direct semiconductor bonded multi-junction cell, which allows us to achieve very high crystalline quality in both the high band gap and low band gap cells. So this is a photograph of the cells themselves and the IV curve for the 38.8% efficiency 1-sun cell. Some other results on the 5-junction gallium indium nitride arsenide cell that we looked at in schematic before is shown here. These are 4-junction cells, IV curves going out to a little bit less than 4 volts. The addition of a nitride cell to form 5-junction cells is very reproducibly showing the increase in voltage that one would expect of about 400 millivolts. This is the quantum efficiency of such a 5-junction cell, where this subcell 4 is the dilute nitride cell. This is the top cell, cell 2, cell 3, the dilute nitride cell. So you can see we're achieving very good quantum efficiencies even in that dilute nitride material. This is the germanium bottom cell, and getting good current densities in all of them. And just to wrap up this sequence on multi-junction cell structures, you can also envision 6-junction cells. This particular example is a 6-junction inverted metamorphic cell, in which the bottom 3 cells are metamorphic cells. We can reach a realistic practical efficiency of over 50% with 6-junction cells like this. And the reason being similar to what we did in going from single-junction cells to 3-junction cells. Going from a 3-junction cell to a 6-junction cell, we're just able to use the photons in the spectrum more efficiently. So we have made some 6-junction cells, and these are measured quantum efficiency curves from each of the 6 subcells. This was an early dilute nitride cell that was not doing quite as well, but we are gaining some experience with these 6-junction cells as well. So these multi-junction cells are implemented into most commonly concentrator photovoltaic systems. We mount them onto a metallized alumina substrate, like in this diagram. So each one is protected by a bypass diode, And then those are integrated into a concentrator photovoltaic system. So one example is shown here. This is a Fresnel lens-based concentrator system made by Soitec Concentrics. You can see the focal point of all of that parquet of Fresnel lenses imaged onto the solar cell material. And these are very thick wire bonds that are interconnecting the subcells, or the component cells. Another way that works quite well for concentrating the sunlight is a reflective dish. These are quite large reflective dishes made by solar systems. And in that case, we have a dense array. There's a parquet of solar cells here. And since all of the solar cells are so close together, that requires active cooling. But it's also a very viable way of achieving large-scale concentrator systems. And it's ironic that just as the sun is setting and these systems are not producing much power, they're at their most beautiful. But so in summary, and taking a look at some future prospects, fossil fuels are contributing to global climate change at a very alarming rate. Multi-junction cells break that Shockley-Queisser efficiency barrier that's imposed by the assumption of a single junction cell by virtue of having more than one bandgap in the multi-junction cells. We do need a wide range of semiconductor bandgaps needed with low recombination, and unifying behavior in semiconductor energy levels offers a way to get to the bottom of what is controlling recombination in these defects across broad classes of semiconductors. And hopefully that will provide a context in which to better understand the low defect recombination activity in certain polar covalently bonded semiconductors in families like copper indium diselenide, gallium indium nitride, and kesterites. So these novel semiconductor materials enable a wide variety of different multi-junction solar cell architectures, and efficiencies over 50% appear to be within our grasp with some of those new materials. The path to 50% efficiency is an important one. In going from 40% efficiency to 50% efficiency, that represents a tipping point in terms of the economic viability of concentrator photovoltaics. So it's a very significant advance. And that opens up wide regions of land area for cost-effective photovoltaics. A lot of the emphasis on higher efficiency solar cells is pushing toward 4, 5, and 6 junction cells because of their higher theoretical efficiencies. We're finding that even though there's a variable spectrum and that affects current balance in those 4, 5, and 6 junction cells, that effect on current balance is more than outweighed by the higher theoretical efficiency of the 4, 5, and 6 junction designs. So new understanding of the defect structure in these semiconductor families, we believe will enable us to apply the multi-junction cell concept, not just for concentrator photovoltaics, but also for one-sun flat plate applications. And that will be a real game changer for the cost effectiveness of solar electricity. So, thank you for coming to the seminar.
Thank you, Richard. That was wonderful. Very good.
Thanks.
Questions? Yeah, Phil.
Questions. One, is it easier or harder to make a higher efficiency cell for space use versus terrestrial use?
Well, the way the spectra work out is that for similar cell architectures, the efficiencies tend to be a little bit lower in space than for terrestrial. So having the spectrum is a little bit redder for terrestrial, and turns out that's a bit easier to convert at one sun.
Secondly, if you look at the economics of the multi-junction cells versus silicon, how do you see it playing out in the next decade or so? It's obviously improved by economics.
Yeah. Well, very good question. It's one that's on our minds, certainly. So I think there are at least these two approaches. One is using the very high quality semiconductor materials that we have today grown by MOCVD and using those in a concentrator system so that if we have a concentration ratio of 500 times, we need 500 times less of that expensive cell area. And actually that reduces the cell cost to the point that it's something like 10% of the overall system cost. It becomes a relatively small part of the system cost. And some of those systems we believe could be the most cost-effective photovoltaic technologies actually for CPV. But even without going to CPV, I think very intriguing to me are some of these concepts where we use lower cost semiconductor materials, polycrystalline compound semiconductors like in the copper indium diselenide family that can be deposited inexpensively in large areas and using those in multi-junction cells. So if we can do that, we can increase the efficiency of flat plate cells above what we can achieve with silicon, and that would be very powerful.
Yeah.
I consulted to Boeing in its CPV efforts a few years ago.
Yeah.
And that effort really wasn't successful because of the complexity of the concentrator, the cooling, the sealing, and everything else that went into the system other than just the solar cells themselves.
Yeah.
So there's an extraordinary complexity, there's layering on top of the solar cell that needs to be looked at.
Absolutely.
Because it's not trivial. Just packaging it is an enormous problem.
Yeah, it's not trivial at all. I couldn't agree more.
So to say this very forcefully, is suppose this solar cell cost 0 cents and was 100% efficient. Right, we're going to use it in a concentrator system. Is a concentrator system still economically viable?
It's not.
So then are we working on the right problem?
Yeah, because just the tracker system, I was designing a tracker system for it, and that's the only part of the project that was successful.
Well, there's a few things I could say about that. One is I think it was 100% efficient, then we might be in business, but it's not going to be 100%.
The concentrator, you just cover the ground.
Yeah, but the other thing I wanted to say was that some other solar cell companies, so Spectralab is a Boeing company, so I'm very excited by that system that you were talking about. But some other concentrator cell companies have, they feel solved some of those problems that you were talking about, some of the problems of encapsulation, problems of control, problems of cell heating. So these are mechanical engineering problems. And some companies, I think, have done better than the specific system that you're talking about and have gone a long way toward improving those systems. But I will say that I think what your example says is that some more work needs to go into the optics, kind of the more conventional materials involving glass, metal, and plastic, rather than the semiconductor materials, in order to make CPV work. Yeah.
Yeah, I don't think the conclusion that it's not economically viable is true. There's surely been a lot of venture capital going into multiple CPV companies over the last 10 years that I think is reasonably smart money, right? So I mean, they certainly see a path there. And Richard actually has written a paper about a year ago on how to get cost-effective CPVs. So you're being modest enough when you sum that up. But I don't think it's a foregone conclusion.
It's a hard problem, but I think some people are doing a good job at solving it.
So how hard is the tunnel junction problem for coupling together the different wavelength cells?
Yeah, very good question. That was actually in the early days of multi-junction cells thought to be a showstopper. And looking back on that, we sort of wonder why did we ever think that? But the tunnel junction cells continue to be a bit challenging particularly for concentrator cells where you might have 500 times the current. For one sun cells, it's quite easy to make a good tunnel junction to pass that kind of current. For 500 suns, it becomes more challenging. And the real challenge comes when you try to make that tunnel junction more transparent so that light can reach the subcell underneath it. So there's always this trade-off between peak tunneling, current density, and the transparency. Transparency usually involves using higher bandgap materials in the tunnel junction, but those higher bandgap materials also increase the energy barrier for tunneling and decrease the tunneling probability. So there's a fundamental trade-off between transparency and the tunneling current. But I think we've been able to make actually some tunnel junctions that can pass with peak tunneling currents that are the equivalent of 35,000 suns. So they aren't the most transparent tunnel junctions in the world, but they are actually, they're acceptable in terms of their transparency because these layers can be made quite thin. So I think the tunnel junction problem is an important one, but we're finding ways to solve it.
Art has a patent on an approach. I don't know if you've seen it.
We've talked about it a bit, yeah.
So.
Yeah, it's very, very interesting.
Another question on patents. So if a new player comes along, to what extent would he be constrained on entering the field by having to work around existing patents?
In terms of semiconductor growth of multijunction cells?
For the whole business. Yeah, if you want to make it.
I think there continues to be new things being discovered all the time. So you may have to rely on some standard technologies. I haven't seen real arduous pursuit of royalty rights or anything like that. People mainly form patents to make sure somebody else doesn't patent it and can keep them from working on it. I haven't really seen a very vigorous patent prosecution environment. So I think they could get into it.
That's because they aren't making money yet.
Well, that may be.
Yes. A lot of the data you were showing for the 500 was at 500x concentration. Is that just because the efficiencies go up and up typically, or is that are you balancing the system complexity? We was talking about tracking is harder as you go up in concentration. I mean, are you guys targeting that because that's a good balance between efficiency and complexity, or what?
Yeah, all the things you mentioned feed into that optimization. So one of the main reasons for concentrating in the case of multi-junction cells is the high cost of these semiconductors on a per square centimeter basis. So by concentrating 500 times, we reduce the cell area 500 times. We reduce the cell cost by, maybe not quite 500 times, but something close to that. So that's one big reason. An additional bonus is the efficiency does go up. So as the concentration goes up, we push those quasi-Fermi levels closer to the band edge, and we get a lower band gap voltage offset, and the efficiency goes up. So that's valuable too. But it's difficult. It starts to become difficult from a practical perspective because of tracking, like you mentioned, when you start getting above 2,000 suns or so. Maybe that can be overcome, but that seems to be 500 suns seems to be a fairly good place for standard concentration at present.
All right, last question. Yes.
Just from an end-of-life perspective, what sort of burden do you see the additional complexity of these multi-junction cells placing on the generation that has to eventually figure out how to break them down, recycle them, or recover them, or at least dispose of them in a responsible fashion? Is it significantly more complex, or is it about the same?
There have been some very interesting studies done on that by a fellow at Columbia. I think what he's found is that it's not. It's actually the issue of sustainability is more complex than one might think. There's a lot of energy consumption involved in making concrete for conventional power plants, which we can avoid in many cases with photovoltaic systems. I think that the small, in concentrator systems, for instance, where the area of cells is smaller, that vastly reduces the problem of recycling those materials or entraining some of those materials into the environment. So I think that it's a very good question. I think a responsible photovoltaics system should involve some type of recycling program, but I think those are problems which we can tackle.
If you have more questions, why don't you come on up and ask Richard, but let's thank him. Great. Well done.
Oh, thanks. Thanks.
Very enjoyable.
Good. I'm glad you liked it.
So
Oh,
I'll
yes.
get this from you,
Okay.
maybe we'll grab
Yeah,
it,
right.
speaker.